Hello, my name is Dr. Tavakoli, and in this semester, we are gonna have Calculus 2 together. For this meeting, I have considered a brief review of some of the materials from Calc 1. So, the title of what we are gonna do today is a brief review of some materials. Of course, we cannot go over everything from Calc 1. Some materials from Calculus 1. So all the students in this class are required to have met the prerequisite requirement of having passed the Calculus 1 with a grade of C or better. So they are eligible to take Calculus 2. Just to refresh your mind, we just have a very brief review of some of the materials from Calc 1. So everything that we do today will be from Calc 1. So they should be very familiar to you. As you have seen in Calc 1, there were two of the important concepts that you have seen in Calc 1. One of them was the derivative of a function. So we had the function f of x or g of x or h of x. You can give any name to the function, or instead of x, you can use any other variable like s, like t, like u, or anything that any letter works as the variable. And you have seen the derivative of the function. One way to show that was, as you might remember, by that prime notation, f prime of x, or d over dx of f of x. Or from the beginning, if I let y be f of x, the derivative is dy over dx. And there are also other notations, as you have seen in Calc 1. And also the other concept that you have seen in Calc 1 was the concept of an integral. And as you might remember, the stretched s is the notation which is used for the integral of a function. As you know, in Calc 1, derivative was the main part of the main thing that was discussed. Also, you saw integrals, but the derivative part was more detailed. You saw more materials from the derivative comparing to integrals. And as you might remember, before derivative, you had the detailed discussion of the limits. And in fact, the derivative was defined in Calc 1 using the limits. Integrals were discussed in Calc 1, but in Calc 2, we continue the integrals. And we see more advanced materials regarding the integrals of functions. Just to make sure that we are all on the same page, let's do some examples to remind ourselves some integrals. As with all the examples that we do in this course, when I write an example, I encourage you to pause the video and try to find the solution on your own. Then you can compare your answer to what I get as the answer here. So as you know, to find out this, we use the power rule of the integrals. The derivative of x, the antiderivative or the integral or indefinite integral of x squared is x to the power of 2 plus 1, which is 3 over 3, and then plus c. As you have seen in Calc 1, for the indefinite integrals, there is a plus a constant at the end, showing that the answer is not just one function, but a class of functions. So when I write this, this means that this includes all the functions of the form of x cubed over 3 and plus some constant. That constant could be positive, negative, or 0. Just as a reminder, in this integral, we used what is so-called the power rule for the integrals. Let me remind you about that. So power rule. It says that indefinite integral or the antiderivative of x to the n is going to be x to the power of n plus 1 all over n plus 1 and at the end plus c. There is one exception to this power rule, and that is when n is negative 1. N cannot be negative 1. Can you see why n equals negative 1 cannot be included in this power rule? As you might have correctly guessed or uh, came up with, when n is minus 1, this denominator right here, minus 1 plus 1 becomes 0, and dividing by 0 doesn't make sense. So this formula is not valid for n equals minus 1. So what should we do for that? For that, we have a separate formula. When n is minus 1, you know that integral or before integral x to minus 1 is the same as what? 1 over x. So for the integral of 1 over x, as you have seen in Calc 1, the antiderivative or the indefinite integral is ln of absolute value of x plus c. So this was the power rule. And this power rule did not work for the case that the power is minus 1. So that's why we needed a separate formula here. And that separate formula was the integral of 1 over x is ln of absolute value of x plus c. If in a problem I know that x is already positive, there is no need to this absolute value. If I know that from the beginning x is positive. So if I have a condition here that x is positive, there is no need to absolute value. But if that condition is not included, we need to put absolute value sign here. Because as you know, with any other logarithms, this makes sense when we have logarithm of a positive number. That's why that absolute value is needed when it's not mentioned that x is positive or negative. So let's practice this power rule a little bit more. Again, everything we do is from Calc 1. So what do you think the answer to this integral is? The integral of 1 over x squared, or antiderivative of 1 over x squared using the power rule. Again, I recommend that you pause the video and do it on your own and then compare your answer with my answer. So here to use the power rule, I should have this as x to something. 1 over x squared is x2 minus 2. That's from algebra, right? From basic algebra, we know that 1 over x squared is the same as x2 minus 2. The reason that I need to write it in this way because I want to use the power rule. The power rule that x to the power of n is on the top is not in the denominator. So that's why I need to rewrite 1 over x squared as x2 minus 2. Then using the power rule, we add 1 to the exponent and divide everything by that, and then plus c. Minus 2 plus 1 is minus 1, so I have x2 minus 1 over minus 1. We try to avoid negative exponents. X2 minus 1 is the same as 1 over x, and this divided by negative 1 just makes it a negative in front of the answer. And x2 minus 1, as I just mentioned, is 1 over x. So that's the answer for this integral. Minus 1 over x plus c. So let me remind you from Calc 1, we have two types of integrals in terms of being indefinite or definite integrals. So sometimes we deal with indefinite integrals, like the examples that we just did. So when we do these integrals, at the end, we have a plus c added to some function. So we find some function that we call that capital F of x and then plus c. And we know that the derivative of the right side is equal to this lowercase f of x. Also, as you have seen in Calc 1, we have definite integrals. Suppose the integral is taken over an interval from a to b. So in this situation, we get a number at the end. As you know, we find one antiderivative of lowercase f, like capital F of x, and evaluate that at the upper limit of the integral. Then from that, subtract that capital F at the lower limit of the integral. And that gives me a number. So from a to b, we have an interval. And when we do this definite integral, we get a number at the end. As you might remember, one interpretation for this number, in the case that the function is a positive function, meaning that the graph of lowercase of f of x, lowercase of f of x is above the x-axis. So if I have a function like this, y equals f of x, assume that a is here and b is here. From A to B for this function, whose graph is above x-axis, the integral gives me the area under the graph of the function. So this shaded region, the area of this shaded region, in fact, is the definite integral from A to B of f of x dx. Depending on the context of the integral, in applications, of course, that integral can be interpreted in different ways. One way, using the areas, it's how I just mentioned that here. Again, this is something that you have seen in Calc 1. Let me do a definite integral example that and ask you to do it on your own before I write my solution. So I recommend that you do this on your own and come up with the answer. This is a definite integral, so at the end you should come up with a number. Simplify the number, but please don't round it unless the problem explicitly says that round to whatever decimal places. If it doesn't explicitly mention that, it means that we need to give an exact answer. Of course, we need to simplify as much as possible, but the answer should be an exact answer. So first I find one antiderivative of x squared. So it's going to be like x cubed over 3. There is no need to plus c, as you have seen in Calc 1. For the definite integral, there is no need to plus c. And this should be evaluated at these limit numbers of the integral, and then we should do the subtraction. As you might remember from Calc 1, the notation that we use here is we draw a vertical line like and with these two numbers. That notation means that I evaluate this function at 3. So it's going to be 3 cubed over 3. And then minus, I evaluate this function at 1. So 1 cubed over 3. So the denominator is 3. 3 cubed, 27. 1 cubed 1, 27 minus 1 is 26. So and 26 over 3 cannot be simplified. So this is the final answer. So the value of this definite integral is 26 over 3. Again, the in terms of the area, the interpretation of this number is the area under the graph of y equals x squared over the interval from 1 to 3. That area is 26 over 3. Okay, let me give another example of indefinite integrals. What is the integral or indefinite integral of radical x dx? And try to use the power rule for this. To use the power rule, we should be able to write radical x as x to something. We can do that because we can use basic algebra and write radical x as x to some power. So as you know, we can write radical x as x to the power of 1/2. So that n in the formula of the power rule, this n here, for the example that we are now working on, that n in fact is 1/2. So using the power rule, x to the power of 1/2 plus 1 all over 1/2 plus 1, and at the end plus c. Of course, we need to simplify this. 1/2 plus 1 is 3/2, x to the power of 3/2 over 1/2 plus 1, again 3/2. Dividing by 3/2 is the same as multiplying by 2/3, right? That's again something that you know from basic algebra. So the final answer, 2/3 times x to the power of 3/2 plus c. So 2/3 times x to the power of 3/2 plus c. And as you know, we can also write this answer in a different format, a different way, using radical sign. So this is going to be radical of x cubed. This is also another acceptable form of the final answer. Either one is fine. Using basic algebra, you know that x to the power of 3/2 is the same as radical x cubed. So either one is acceptable. Now let me give a definite integral example for the same function. Please try that on your own and let me come up with an answer in fact, with a number. The integral from 1 to 4 of radical x dx. The previous example makes our job a little bit easier because we know that what is antiderivative of radical x, as we calculated in the previous example, antiderivative of radical x is 2/3 x to the power of 3/2. And now this should be evaluated at those limits of the integral. What does that mean? It means that that antiderivative that we have just got should be evaluated at 4. So 2/3, 4 to the power of 3/2 minus 2/3, 1 to the power of 3/2. This is simple because 1 to any exponent is 1. 4 to the power of 3/2, 4 to the power of 1/2, like radical 4 is 2, and 2 cubed is 8. So this is equal to 8. So let's see what we have so far. 2/3 times 8, which is 16 over 3. And 2/3 times 1, just 2/3. And the answer is 14 over 3. This fraction cannot be simplified more, so we just leave it as it is, 14 over 3. So this tells us that the area under the graph of radical x over the interval from 1 to x equals 14 over 3.